Let's start and welcome to this second day of our operator algebra conference. And today it's my pleasure to start with Ivan Bardet from Inria Paris. And today he will speak us about approximate tensorization of the quantum relative entropy. Thank you, Ivan.
Okay, thank you, Rafaela. So my talk will be about approximate tensorization of the quantum relative entropy, and it's based on joint work with Cambyse Rouset and Angela Capel. They are both in München. So before starting, I wanted to share a souvenir. So I had the opportunity and the chance to meet Wolfgang Jones 10 years ago. So it was at Château des Goutelas in France during a weekend, and he gave a lecture during 2 days on not polynomials. I really appreciated his lectures, and I remember that it was very surprising for me that such a difficult topics he made it so understandable, it's so enjoyable. And I was just a master student, so it was really a great opportunity to meet him at this point. So you can see him. I don't know if you see my mouse when I move it. So you can see.
It. Yes.
Yes.
So you can. Okay, great. So you can see Jones in the middle, and I'm just here, and I'm sure you can recognize several other mathematicians in the group. Okay, so I will start with the context of the result I want to present. So let me first introduce commuting square of finite-dimensional algebras. So I start with 3 algebras, M, N1 and N2, that are both subalgebras of such, bigger algebra N. And I will assume that M is the intersection of the two others. And for me, I will really restrict to finite-dimensional normal algebras. And because I'm on a finite-dimensional space, states are given by density matrix. So I will assume that sigma is a density matrix on the Hilbert space H. So it's a positive operator with trace equal to 1. And in my talk, I will always assume that sigma is compatible with the 3 algebras. By this, I mean that it will the modular operator defined here leaves the 3 algebras invariant separately, of course. And because of this, and thanks to operator algebra theory, we know that there exists 3 unique conditional expectations going from n to one of the 3 subalgebras. And so this conditional expectation is compatible with the state or the density matrix. And by this, I mean that we have this condition. Okay, and so in this context, a commuting square is the data of these 4 algebras on the states. And we ask that they verify this condition. So when we compose the conditional expectation on N1 and N2, in whatever order, we obtain the conditional expectation on their intersection M. Okay, so I think there are a lot of experts on operator algebra in this audience. They know way better than me this definition, but I think it's not the original definition, but it's almost straightforward to prove that it is equivalent to this.
Just a tiny question. You wrote sigma is greater than or equal to 0.
Yes.
So are you assuming it's faithful or not necessarily faithful for the rest of your talk?
Good question. Yes, I forgot to mention that it will be faithful. So here it's not important, but in the next slide it will be.
Okay, thank you.
Sorry, so yeah, it's faithful. So it is invertible. Yes, thank you. Sorry for I forgot this. Okay, so so I start with a commuting square. So M, N1, N2, and sigma. Thanks to this, I have conditional expectations. Just as a notation, I also introduce the predual. So here, because I'm on a finite dimensional space, the dual is defined thanks to it's also the dual, and it's thanks to the trace, the duality given by the trace. Okay, and a very important result in quantum information theory. So it was proven first by Petz in 2007, and then by a few years ago by Li Gao, Marius Junger, and Nicolas Larapuente in 2017. So given a commuting square, we have this tensorization of the relative entropy. By this, I mean that when you measure the relative entropy between rho and its projection on M, it is smaller than the sum of the relative entropy of its projection on the two other algebras. So for those who don't know the definition of quantum relative entropy, it is given here. And it is the finite dimensional version of the quantum relative entropy defined by hierarchy in the context of fundamental algebras. Okay, and the purpose of the talk on this presentation is to address the question, what can we say when this algebra don't form a commuting square? So before focusing on this question, I just want to give two examples where we have commuting square. The first example is one of the most well-known inequality in quantum information theory. So it's called the SSA inequality for tripartite states. So I start with a tripartite system. So it's tensor product of three-dimensional Hilbert space, HA, HB, and HC. And I also have a density matrix sigma, which is also the tensor product of three density matrices. So faithful or invertible density matrix. And as conditional expectations, I will take the partial trace with respect to either system A union B or system B union C or B. And this leads to the following commuting square. So N1 is the Hilbert space defined by system A and B. N2 is defined by system B and C. Sorry for the mistake. And M is the intersection, so it's only system B. And just remark that in order to have a commuting square, so in order to have conditional expectations, we need the state to have this product structure. So I can, because it is so you can really check that it is a commuting square. And thanks to this, we have the tensorization of the quantum relative entropy, which in this case read like this. So when I write rho B or rho AB, it means the trace with respect to the other systems of rho. Okay, so I end up with this very nice inequality, and you can just develop it thanks to the definition of the relative entropy. And you end up with what is known as the SSA inequality, which is an inequality between von Neumann entropes. So von Neumann entropy is defined here. And this is really one of the constants of quantum information theory, that you cannot do quantum information theory without this inequality. Okay, so just to restate this inequality, so we can define as a quantum mutual conditional entropy, which is defined like this. So it's the sum of two entropy minus two other entropies. And the SSA inequality states that this quantum mutual conditional entropy is positive. Okay, and so one question that we can ask is what happens when it is zero, when this quantum mutual conditional entropy is zero. So let's assume that sigma now is not a tensor product of three density matrix, but it is such that its quantum mutual conditional entropy is zero. And we know what is the structure of such states. So if we have such a state, the system HB, it can be decomposed as like this. So this is only for B. Okay, so I guess you recognize this kind of decomposition. So it's just the sum, so the direct sum, sorry, of tensor product between what I call a left part and a right part. And when you have such a, so when sigma is a quantum Markov state, so when its quantum mutual quantum conditional mutual information is 0. We know that it can be written in this form. So it's a block diagonal according to this block to these blocks. And in each block, it is a tensor product between two different matrices, positive matrices. Okay, and according to such a decomposition, I can define a commuting square. For N1, I take the left part of each block, and I take identity on the right part. For so here I also take the tensorization with system A and tensorization with system C, of course. So for N2, I take the commutant of N1. So I take identity on the left part and the whole space on the right part. And thanks to the structure of sigma, thanks to the decomposition of sigma, we can prove that this forms a commuting square. So I didn't write the corresponding tensorization, but because it would be the same inequality. And this is another example of tensorization of relative entropy that this generalization of this SSI inequality allows to prove. Okay, so my goal now is to study a generalization of the tensorization that I call quasi-factorization or approximate tensorization. And it is almost the same inequality, but in front of the right side, I multiply by a constant C. So C is a positive constant. I will not explain what it is now. I will come back to this later. So again, we are exactly in the same context. So M is a subalgebra of N1 and N2. It's also the intersection of the two algebras. And sigma is a state on M, and it is compatible with the three algebras in such a way that there exist unique conditional expectations compatible with sigma. So, okay, so why do I want to prove such an inequality? So the motivation comes from the commutative case. Because we know that when N is commutative, so recall that N is the biggest algebra. So when N is commutative, first, all the other algebras are also commutative, of course. And we have such an inequality. So the constant I end up with here is 1 over 1 minus 2c. Again, I will come back to what is this C later, but I just want to say here that C is a measure of correlations between the two algebras N1 and N2. And why I'm interested in such an inequality? Because it is one of the main tools in classical theory of spin systems in order to prove log-Sobolev inequalities. And in the quantum case, in the case of quantum spin systems, there are very few examples of systems where we can prove log-Sobolev inequalities. So what I'm interested in is proving this kind of inequality for quantum spin systems in order to prove log-Sobolev inequalities. And this is very important to have this motivation of log-Sobolev inequalities behind, because we cannot afford any inequalities. Like it will be a guide in order to know if the quasi-factorization we obtain is what we want or not.
And just so I understand this goal clearly, you're focusing on finite-dimensional systems, but
yes,
your hope is that eventually, once you get to these quantum spin systems, you'll be able to understand these log-Sobolev inequalities there?
Yes, exactly. So I will come back to this at the end, but so it will stay finite-dimensional system, but we will be interested in increasing the size of the finite of the system, increasing the dimension of the system. And we want the log-Sobolev inequality to be constant, to be born independently of the dimension of the system.
Great, thank you.
Yeah. So basically, this inequality will allow to reduce to smaller dimension. Okay. Okay, so the outline of my talk is the following. So first, I want to explain a bit more what is my motivation. And for this, I will focus on one example of, I will focus on the simplest example of spin systems when there is no interaction between the different spines. And so this will be my third example, and I hope it will become clear why I need quasi-tensorization after this. So then I will focus on my main result on quasi-tensorization. I will keep it in a very abstract form. And in the last section, I will focus again on quantum spin systems. And I will show how my result in the abstract form can be formalized in this case. Okay, so the first part. So let me introduce the simplest example of Markovian dynamics in a quantum spin system. So I start with, to make it a bit more physical, I will give some definitions. So I start with a self-adjoint operator on H that I call, of course, the Hamiltonian. And the Gibbs state at inverse temperature beta is given by the following density matrix. Okay, and so the simplest Markovian evolution that I can define, which project on this Gibbs state, it is called the depolarizing channel, and it is given by this form. So here you can see directly that it suppresses exponentially fast any x, and similarly, it creates exponentially fast the state sigma beta. Okay, so this is just, for me, this is just one copy of the system, but I'm interested in spin systems. So I'm interested in n copy of the systems. So I introduce the Hilbert space H tensor n, so it is n copies of H. And the Gibbs state on the spin system is just the tensor product of the Gibbs state on each system. And the dynamic that I want to study on this spin system is also the tensor product of the single site or single spin dynamic. And what I want to prove for such spin system is the following inequality. So I want to prove that there is exponential decay of the relative entropy. So I know that my PT of n, it will converge toward my Gibbs states. And I want to prove that this convergence is exponentially fast in relative entropy. And what is well known in classical theory, and also what is very well understood now in the quantum case, is that in order to prove such an inequality, it is enough, or it is even equivalent, to prove what is called a modified log Sobolev inequality. So, which is this inequality where EP stands for the entropy prediction, and it is the derivative of the relative entropy at time 0. And you can see that both inequalities are equivalent, because it is, in order to get the second one, it is enough to differentiate the first one. And in order to get the first one, it is, you just have to integrate the second one. Okay, so my goal is to prove such inequality, and what was proved very recently, so 3 years ago, by 2 different groups. So Angela Capel, Angelo Lucia, and David Perez Garcia from one side, and Beiji, Data, and Rosé from the other side. What they prove is that the log Sobolev constant for such a system, for such a spin system, does not depend on n, does not depend on the number of copies. And here we can prove something more. We can even prove that it is bounded by 1. Okay, let me give you a sketch of the proof of this. So the first step is to reduce to one site. And in order to do this, I use the SSO inequality, or more precisely, I use tensorization of the relative entropy, which I recall is equivalent to the SSO inequality. So I just apply this inequality to the relative entropy, and I find that the relative entropy between rho and sigma and the n copy of sigma beta is smaller than the sum of the two relative entropies. So here what I did is I trace here the n-1 copies of the system to end up with rho h1. And for the first relative entropy, and the second one, I do the reverse. So I trace only the first copy. Okay, so I use this SSA inequality once, but I can repeat it again with this relative entropy. And at the end, I end up with with the sum of n relative entropies. And what's interesting in this relative entropies is that now the state rho, it appears only in one system. So, okay. And this is why I say that we reduce to n copies to 1 copies. Okay, so now I want to prove, so let me recall what we want to prove. We want to prove this inequality. I reduce this relative entropy to a sum of n relative entropies. So now I want to study this right term, this entropy prediction. And what you can prove directly, so I will skip the computations, but what you can prove directly is that it is linear and in the number of copies. And so it is a sum of entropy prediction for each site, which is defined this way. So maybe don't look at this ugly expression. But just what you have to understand is that this is really the entropy prediction for one site. Maybe what's important here is that, is that the evolution only appears on one site and it is identity elsewhere. Okay, so now what we are left to prove if we use both equations is that one relative entropy is smaller than one entropy prediction. And I just wrote it for site 1 because by symmetry, all this inequality are equivalent. And now this is just a matter of computation because you can directly compute what is the entropy prediction for one site. And it is just the sum of the relative entropies that we want and another relative entropy, so the symmetric one. And so it is greater than the relative entropies that we want. Okay, just to summarize what we did. So we wanted to prove log-Sobolev inequalities for n copies. In the first step, we reduced to 1 copy. And in the second step, we proved the log-Sobolev inequality for 1 copy. Okay, this is what I wrote here. And what is important here is that reducing to from n site to one site, we use the SSA inequality. So we use tensorization of the relative entropy. And then proving, so in the next step, we prove log-Sobolev inequality for one site. More precisely, we prove a complete version of log-Sobolev inequality. And so quantum log-Sobolev inequalities for spin systems, it has been an open question for maybe 20 years. And this is really the first result that people got, and it was only 2 years ago. And what we understood from this example is that those two steps are really important. First, an inequality regarding relative entropies, and then a proof of complete log-Sobolev inequality. So this has really been the roadmaps that we have been working on in the last few years. Okay, and in the first, so this complete log-Sobolev inequality, I only prove it for one example for the depolarizing channel. And this was really a very simple example, but it was an open question for the last 3 years if we could prove such an inequality for general Markovian dynamics. So in the last section, I will focus on a particular quantum Markovian dynamics, which are called Davies quantum Markov semigroups. And Ligao and Camby's-Rose proved this year that this complete modified log-Sobolev inequality is always true for such dynamics. So now, if we want to prove log-Sobolev inequalities for spin systems, what is still unknown is the first step, trying to reduce from n sides, n spines, to one spine. And so we have our roadmaps. We know that if we can prove approximate tensorization of the quantum relative entropy, we will be able to prove log-Sobolev inequalities for quantum spin systems. Okay, so let me just check the time. Okay, so now let me introduce the result on approximate tensorization or quasi-tensorization. So I just recall the context. So I have 3 algebras M, N1, and N2. I have a density matrix compatible with the 3 algebras. So I have also 3 conditional expectations and their predival. So as a short notation, I will write rho G for the projection and rho G of rho M the projections on the corresponding algebras. Okay, sorry. So now the inequality I want to study is what I call approximate tensorization or quasi-factorization, and it's reduced to this inequality. Okay, in order to prove this inequality, the strategy will always be the same. I want to use the following lemma. So there are a lot of notations, so maybe don't focus too much on the notation, but what is important here is that this is like, if you look at the first 3 relative entropies, if you look at the left of my mouse, this is the tensorization of relative entropy. So here I just correct this tensorization with a term, so logarithm of a scalar product. And my scalar product is defined thanks to this word integral. And here I also use a small notation, so the xi's are the relative densities. Okay, so this is already a kind of approximate tensorization, but with a additive correction. So just I want to explain why there is this weird scalar products. So this comes from the Leibniz extension of Golden-Thomson inequality. So it's a comparison of exponential of matrices, but with 3 terms. And what Leibniz proved was that you have this inequality and with a super operator, so with an operator on matrices that involves this this integral. Okay, but I just wanted to explain why there is such an expression, but really what matters here is that we have an additive correction of this form.
I noticed that this is the rotated Petz recovery map essentially, but doesn't the
yes, exactly. Yes.
doesn't the modular group condition hold? Because are you assuming that your conditional expectations also transfer the states?
Sorry, I don't understand what you mean by this.
Are your conditional expectations state preserving?
They preserve the state sigma, but yes, of course, they preserve the state sigma. This was my main assumption. So let me come back to this. So sigma is a density matrix compatible with the 3 algebras, and the conditional expectations are defined thanks to sigma. Yes.
I see. Okay, thank you.
Okay. Okay, so thanks to this lemma, I can prove my first approximate tensorization results. And here I will focus on the case where M is a trivial algebra. So in this case, we know that so sigma becomes the unique invariant state because M is trivial. And so the conditional expectation, or its peridual, project on sigma for any density matrix. And then what we can prove is the following approximate tensorization. And you can see that it's very similar to the classical case. And here, C, as you can see, is a measure of how far the composition between 2 conditional expectations is, how close it is, from M. And it is in L1 to L infinity now. I will give a very rough sketch of the proof. I just want to explain why this constant, why does this, where this constant comes from. Of course, okay, so let me recall the expression for the lemma. And what is a simple computation is the fact that the conditional expectations, they are self-adjoint with respect to the scalar product that I defined before. So thanks to this, we can reorganize this scalar product. First, I subtract identity. And so I subtract it both times, so I have to add it once. Okay. And because the conditional expectation are self-adjoint, the conditional expectation, which is on the left-hand side, I put it on the right-hand side. Then I have this expression. I can just use Hölder inequality between L1 and L infinity space. And then I use the definition of what is L1 to L infinity now. Okay, and now I'm very close to, sorry, I forgot to add +1 here and here on the last two equations, sorry. And then to go from here to the results, it's just a matter of applying Pinsker inequality, which states that the one norm is smaller than square root of twice the relative entropy. Okay, just again, what is important here is that what pop-ups is Holder inequality between different norms. Okay, so for spin systems, this constant is very interesting because it measures the correlation between two different subregions of the lattice of the systems. And in the non-alternating case, what we saw is that the constant is equal to 1. And also, what is known in the case of classical spin systems is that this constant decreases exponentially fast at high enough temperature. So above a certain critical temperature, we know that we have an exponential decay of this constant in terms of the relative distance between two subregions. And this is known as exponential decay of correlations. And also, what is one of the most important results in the study of spin systems, in a study of convergence of spin systems in the classical case. So what is done in the classical case is that exponential decay of correlation, so this condition, is equivalent to the modified Sobolev inequality. Okay, so okay, I already gave a very sketchy proof, but the proof I gave, it's still true when M is not trivial. I never use the fact that M is trivial in the proof. But in this case, when M is not trivial, we don't have a control on this constant. In particular, in quantum spin system, we will need to tensorize the system with the algebra with any copies of d by d matrices. And if we do that, and if we look at the constant we end up with, we know it will go to plus infinity. And that's why I say that we have to be focused on our main motivation, which is proving Sobolev inequality, because we know that this result, when M is not trivial, will not be enough to prove Sobolev inequalities, and we need M to be not trivial. And to summarize this, what we need is a complete form of approximate tensorization, so complete in the sense of operator space theory. And the result we have at the moment does not allow it. So I think I will have to go a bit faster. Sorry. So now this is what I want to propose as an alternative form in the case where M is not trivial. So first we know the structure of any finite-dimensional von Neumann algebra. So we know that for such an algebra, we have the decomposition of the Hilbert space H in the form of direct sum of tensor product of two spaces. And we know that M is as this form. So in each block, it is the whole algebra on the left side and identity on the other side, the right side. And because we ask that sigma is compatible with M, we also know that sigma has such a structure. So it can be decomposed according to this decomposition of the space. And in order to prove approximate tensorization, I will assume this very rough hypothesis. So I must say that I'm not very satisfied with this hypothesis. First, because I don't understand it very well, and also because I would prefer more direct hypothesis, like using operator space theory or whatever. But for the moment, this is what we have, and this is also what will allow me to prove approximate tensorization for certain examples. Okay, my hypothesis is the following one. I want to assume that when we compose the two conditional expectations, maybe you can focus here. First, we cut the off-diagonal terms in the decomposition of M. And second, we also cut all correlations between the left system and the right system. And so this is a very strong hypothesis, but as I said, it is enough in some examples, and I think it could be enough in more examples. And with such an hypothesis, we can prove, again, the same kind of inequality, but what is modified is just a constant. So the correlation constant C, which is almost the same as before, but now I focus not on the whole conditional expectation, but just how they reduce on the K alpha copy of the system. Okay, so it is included in my hypothesis that the conditional expectation reduced to this part of the system, and then I can prove approximate tensorization using this correlation constant. Okay, so let's see how this works for quantum spin systems. So first, let me define what is a quantum spin system. So I start with a finite lattice, lambda, which is a finite subset of ZD. So you can think of a big hypercube in ZD. And my quantum system is just the tensor product of copies of HG. So I put HG on each side of lambda. So given such a quantum system, I define R local potential. So it is a map from lambda to the operator on H lambda. And each operator phi of G, it is self-adjoint, and it is supported in a ball of radius R centered on G. So if I knew how to draw pictures on Brimmer, I would have done it, but you really have to think that phi of J is a Hamiltonian acting locally on the system. And one of the main assumptions I will make is that this potential phi is a commuting potential. It means that any two potential for two different sites, they commute. And thanks to this potential, I can define my full Hamiltonian on the system, or rather on a subregion of the system, which is the sum of all potential inside the subregion A. And also, now that we have a Hamiltonian, we can, of course, define the Gibbs state, which is given by this density matrix. Okay, so I will make it short. So on such quantum spin systems, we can define what is called quantum Markov semigroups. So I don't want to define them because it involves a lot of notations. But what is important is that there are a family of completely positive and unital maps. Also here, I define such quantum Markov semigroup for any subregion A. Also, thanks to the very definition of Davies quantum Markov semigroup, we know that the Gibbs state is an invariant density matrix for all those families, independently of A. Also, this quantum Markov semigroups, they have what is known as the return to equilibrium property, so they converge towards their fixed point algebra. I don't need to define the fixed point algebra because in our last paper with Angela Capel and Camille Rose, when we studied approximate tensorization, we also prove a result on the structure of this fixed point, and it's given by this. So it is a commutant of a set, and the set is defined as all operators on a site A. And then you apply the modular group to this, to all those operators. And what you can see here is that this inside is the smallest algebra that contains B of HA, and that is invariant by the modular operator. and the fixed point algebra is the commutator of the sets. Also, by definition of Davies Cantor-Markov semigroup, we know that this algebra is compatible with the Gibbs states. And so it defines uniquely these conditional expectations. And they are compatible with respect, of course, with respect to this algebra. So this is the algebra I want to study. This is the algebra with respect to I want to prove approximate tensorizations. Okay, so I can do it for two examples. So the first one is like the simplest example you can think of, and it is classical potential. Basically, it is just a classical Hamiltonian that you can embed in the quantum system. So what I mean by this is that you start with a classical Hamiltonian, you choose orthonormal basis of your system, and you wrote this classical Hamiltonian in this orthogonal basis, orthonormal basis. And it also means that all the phi j's, they can be diagonalized in the same tensor product orthogonal basis. Okay, and the second example is a class of two local Hamiltonian, and two local means that each potential they only act on two sides or two spins of the system. And for these two examples, we can prove the following. First, we can prove that at infinite temperature, so when beta is equal to 0, if you take any A and B, then you have a commuting square. And so because you have a commuting square, then you have the exact tensorization of relative entropy. So this is straightforward for classical Hamiltonian because it is true for classical systems. And the conditional expectation is more or less the same as for classical system. So what is new here is that it is also true for two local potential. And what we also proved, so we prove it for classical system, and the case of two local systems is a work in progress. So what we prove is a version of approximate tensorization for these two examples. So it is again the same inequality with the same constants. And here omega index the decomposition of the fixed points for the biggest algebra. Okay, so maybe what I forgot to say is that when you take the intersection, the union of A and B, then the fixed points is the intersection of the two fixed points for A and for B separately. So they really form so they are compatible to study approximate tensorization. Okay, so let me conclude. So we have proved approximate tensorization for the quantum relative entropy. In the case of classical Hamiltonian and two local Hamiltonian for quantum spin systems. And these two results of approximate tensorization, they lead to a new proof of modified log-Sobolev inequalities for quantum spin systems. And I think, I'm not sure, but I think they are the first two examples of such proofs. Apart from the non-entropic case, of course. And so here I use approximate tensorization, but in the previous paper in 2020, so Capel, Rosé, and Silfranca, they directly prove the log-Sobolev inequality using almost the approximate tensorization, but they had to make a very tricky geometric argument. It's a very long argument. And so now we have a very direct proof, which is the same as in the classical case. And it's also very interesting because it proves that for the first time, it proves that the approximate tensorization inequalities, there are a possible strategy in order to prove MLSI, because before that, we didn't even know if it was possible to use the same trick, the same proof as in the classical case. Okay, so now what I'm working on and what I will do in the future is, of course, try to understand this. Oh, sorry, I forgot to say that. Sorry, so let me go back to this theorem. Of course, in order to prove approximate tensorization here, what I do is I check that this condition is true, that this ugly condition. And this involves like studying the structure of the fixed point, more or less. So what I want to do now is have a better understanding of this condition. In particular, what I would like to do is I would like to prove that this condition is true when at infinite temperature we have a commuting square, because I know that it is true for the two examples, and I really believe that it will be true in general, that commuting square at infinite temperature is a correct assumption in order to get this condition here. And also, as I said, it is a very, I don't like that we need the structure of the fixed point or the fundamental algebra M in order to study this condition. I would like a more abstract definition. I think the correct way to do it would be to use operator space norms on amalgamated norms. And so we have been working on this also recently. Okay, so thank you for your attention.
Thank you, Ivan. And if there are some questions, please. Is there anybody?
I have another question. I kind of wanted to understand the physical interpretation of considering these three different subalgebras, M, N1, N2, and N inside of this larger space in the context of spin systems. Were you, I can't remember, were you assuming that N1 is not necessarily in the commutant of N2 and vice versa? And you were allowing...
It is very important that they are not in the commutant of the other one, because if it is the case, then you have a commuting square.
Right, okay. And so part of this idea was exactly generalizing to that situation where they don't necessarily...
Yes.
Okay.
So
great.
basically, the situation is really this one. So you have the whole lattice lambda, and inside you have a subregion A. And so you have two subregions, A and B, and N1 is the projection more or less on A, and 2 on B, but they are overlapping. Of course, they need to overlap. It is very important that they overlap. And so you want to prove if they don't overlap, if A and B don't overlap, then you have a commuting square. If they are far away enough, you have a commuting square. So what we want to prove is approximate tensorization when they overlap. Yeah. Thank you.
And I also have a little question. So you have worked with relative entropy and aim to prove the modified log Sobolev inequality, but this tensorization can work also for let's say the L2 entropy, and so for the log Sobolev inequalities, not modified. So in order to have hypercontractivity, do you think?
So it's a very good question. So let me go back to here, yes. So exactly. So here we focus on modified log Sobolev inequality, which is a kind of L1 log Sobolev inequality. And the most well-known log Sobolev inequality is the L2 log Sobolev inequality, which is equivalent to hypercontractivity. So if we wanted to follow the same two steps in order to prove hypercontractivity or log Sobolev inequality in the L2 case, we will have to prove a complete version of this inequality. And with Camby's-Rose, we already proved, I think it was 2 years ago, 3 years ago, that the complete version is never true in the quantum case.
Okay.
So we know because of this that we cannot use the same strategy. So it's not completely right. So we have a weak version of hypercontractivity, but the problem is that it introduces a weak an additive constant, and in the first step, this additive constant, we cannot control it, and we think we don't know of a way to control it.
Okay, thank you. And are there any other questions? Otherwise, we thank Ivan again. Thank you.
Thank you.